Draft physics video. Yay. Anyway, so parapolylogic, whatever, um, left a comment about this new gravitational wave thing they found, where they have confirmation because they see it as well as, whatever, feel it or hear it or whatever the silly metaphors are. Yeah, I hadn't heard about it, and he liked my opinion, I suppose, but I'll give my opinion anyway. Yeah, lots of questions. They're not going to answer all the questions that need to be answered, unfortunately. I should have it here. Yes, first ever. All right, so we might as well start at the beginning. So this is a Veritasium video.
Gamma ray bursts have been
yeah, it's for decades.
in order to detect gravitational waves.
Yeah, here we go. Okay. So we'll bring up the volume a little. Try to get the facts and such. So let's see if we can start at the real beginning.
Technological challenges that had to be overcome in order to detect gravitational waves. Some people were
skeptical. Yeah, because this whole conversation evolved out of something a long time ago with Einstein. So the question was, we knew that there was these pulsars, the blinking stuff out there. And the question was posed to Einstein, would gravity blink? So when two things go around each other, say the red one's the lit object, there's a point where the red one's behind the black one and it blinks off. The light turns off. And so the question sort of was, when they're lined up, would gravity do the same thing? Would it blink on, so to speak, in terms of being stronger when the two things were lined up, and then weaker when the two things were apart from each other? Now, back in those days, they didn't speculate that things would be so close together and be spinning, many thousands of times a second or whatever they're up to now. Maybe they're up to millions. And so anyway, so Einstein said, yes, the gravity would change. You could have a wave in the sense that there would be a difference in the gravity, but you'd never be able to detect it just because how you can't see. From a distance, you can't even see two objects as distinct objects. It all blurs into one, and it's the same amount of energy, and so you would never be able to detect a gravitational wave. So that's where it started. That's the conversation it started with. Now, somewhere in the process, they invented this new concept of a gravity wave, which was, we're going to convert the matter of these objects into whatever the medium is that makes the bent space phenomenon happen. We're going to convert physical matter into gravity, quote unquote. That's not a conversation Einstein had, as far as I know. If somebody has evidence of Einstein talking about making gravity out of mass, converting a mass into bent space, please link me to it, but I didn't see it anywhere in what I've read. And so I don't know who invented it, someone except one of these LEGO people. So this is their concept, that somehow you can do this, and that this force, this disturbance in the bent space, travels through space at the speed of gravity, the speed of light, and somehow, as a force, it's benign. So like gravity goes through us, it's kind of benign. A little extra gravity we ain't gonna notice. But if you add up the amount of force, gravity's pushing us down towards the Earth. It'd be a lot of force. So for photons, you can imagine, take a lot of photons to push you into the Earth, as hard as the gravity's pushing you into the Earth. So by comparison to photons, the gravity's pretty benign for us. But it's a tremendous amount of energy to shake the Earth, and for us to see the difference in how much the Earth is shaking over here compared to how much it's shaking over here. That requires a tremendous amount of energy, and that is ignored in all these conversations. That if I converted it into photons, it wouldn't just crush me or smash me or incinerate me in a second, which it would do. Not now. Busy. Um, it would just be so it's just coincidentally lucky that these massive events that happen in the universe just happen to happen with a force that doesn't burn us to a cinder. But if we converted the amount of energy, like I said, into actual photons, it would, even from 100,000 light years away. So anyway, just a little context.
Skeptical that scientists had actually done it, that they'd actually seen gravitational waves from black holes. After all, there was no corroboration. But after the discovery that's being announced today, there can be no more doubt.
Right, so just more, of this propagandizing, like there's, the theory somehow is correct, and it's undeniable, and we can prove it with all these coincidences, and that's, that's all this is.
Because scientists have detected the merging of two neutron stars 130 million light years away.
Okay, so let me write that one down. So this one's much closer. So instead of being 5 billion light years away, this one's only 100, what did he say, 130 million. You say million? Got to make sure we get it right, Gary.
Stars 130 million light years away.
Okay, 130 million instead of 4 or 5 billion. So I'll have to figure out what percentage of 5 billion this all comes out to. Light years, okay. Continue.
This is the first ever detection.
Okay, so this graphic doesn't have anything to do with this event because we don't have any evidence that it did this, whatever these emissions are. We don't have any evidence that that happened.
Of gravitational waves from in-spiraling neutron stars. And what's really exciting about this detection is...
So all that's just made up. Alright, so there's something really exciting about this detection. Okay, when we get to the facts, then we'll say there's a lot of things weird about this detection.
Is that the same event has been observed with telescopes in all areas of the electromagnetic spectrum.
So somehow the telescopes saw more X-rays, more ultraviolet, more infrared, more radio, and more gamma rays. They saw it, and we don't get any evidence that any of that happened, though. None's provided.
It all began on August 17th at 8:41 a.m. Eastern Time, when LIGO interferometers identified a clear gravitational wave signal that lasted about 100 seconds.
Okay, so they only have 50 seconds here, and so it lasted 100. So here's the other detections. Tiny things, right? I mean, this is the first big one, and it was happened all in less than 1 second. The whole event happened. Two massive black holes spiraled into each other in less than 1 second. The whole event happened. And they were massive by comparison. 30 solar masses. These neutron stars are barely a little bit over a solar mass. So just look how small that stuff is. And all of a sudden this, and they have to double the scale. It's not even half as long as it should be. And these had this dramatic chirp, 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 chirp. No dramatic chirp at all. Just a slow rise in the thickness of the line. So, okay, yeah, this is all about the same stuff now. So we haven't changed the game at all, right? This isn't a completely different game. Okay, I didn't even think they were listening to those things. They didn't even set any of the computers to do anything over a second long because that was all part of their theory. And so, but apparently they decided to put some computers to the job of go find us a signal that takes longer. And they found one. Sorry, come on. Anyway, let's continue.
Which is way longer than any previous detection, and it's consistent with theoretical predictions for this.
Right, theoretical predictions by who? The LIGO people. Who else did any of this theorizing? In any of these theoretical predictions that anybody predicted, who besides the LIGO people did the predicting? Where's the conversation in physics? Where are the publications demonstrating how this somehow is a phenomenon that the evidence before LIGO indicates exists? that any other evidence in the universe besides LIGO indicates this exists. Alright, there's no theoretical evidence besides their own and their own results. So the whole thing is just something in-house. We don't need any other science to verify it. It's pathetic.
Signal from two merging neutron stars. Around.
Oh, and then they played this sound, right? That's the sound from this, okay? You can't say this sounds exactly like this, okay? That's just propaganda, okay? So that's just playing games with the facts. We don't care. We'll just play the same sound effect and present that. Oh, they all sound the same, except they don't look anything like each other. So, yeah, just cheat the truth some more. Who cares? It's only the truth.
1.7 seconds later, NASA's Fermi Gamma Ray Telescope identified a burst of gamma rays.
Right, now, we're not going to be told how often that happens, you know, the burst, and how long the burst lasted. But the key thing is 1.7 seconds later. So 1.7 seconds later, that is, there's no real time delay. There's only a picosecond time delay between hitting, Washington State and hitting New Jersey in terms of light traveling. It's a tiny amount of time. So 1.7 seconds. There'll be no accounting for why it's 1.7 seconds. So the whole event happens. The supernova crashes. It releases this tremendous amount of energy. I mean, it converts. I don't know. Somewhere there's got to be a rule of consistency, right? I mean, if Einstein's right that you can't destroy energy or mass, then you've got to convert it. So we can call it energy, right? These waves of energy, there's some sort of positive energy, some sort of positive wave, not a negative wave, but some sort of positive wave of stuff. Okay, so I would say they could be tons of some kind. Something not at a frequency. That would be real energy anyway. So that might be believable. But what's not believable is somehow you can release that gravity energy before, you release the light energy. Because rationally you can sort of understand that what has to degrade, what has to get ripped apart for you to release gravity waves would be electrons and protons. You'd have to be shredding those. And the fact is long before you're shredding those, you'd be shredding the energy between them, which is the photons, the things we can see. So the light should come before the release of the tougher to release, obviously, the converting thing, the thing that requires a conversion. When you release photons, you're not converting matter, you're just letting the energy go, and the matter bits, the electrons and protons, stay together. But if you rip electrons and protons to pieces, if you tear them apart, then you can make this new kind of energy, this bent space stuff. But again, so he doesn't say anything about why it's 1.7 seconds later. Because, frankly, what are you going to make? An excuse? You're going to say their clocks aren't adjusted right? They're scientists, but they're not using the same standard time. What's the excuse going to be? The event happened, and then the black hole, the neutron stars all blown up and ripped to pieces. They just sat around for 1.7 seconds and says, I'm tired. Oh, I forgot, I have to make a whole bunch of light. And then they decided to make the light. Is that how it goes?
For decades, gamma ray bursts have been thought to come from neutron star mergers.
See, they just went right over that little how long it lasted. Didn't last very long, did it? No, little burst didn't last very long. Okay, so anyway, so you had this little burst of the gamma rays after the chirp. So this is how we're supposed to believe these events happen. It does a little zoop, chirpy thing, and then it waits a little while, and then it goes bloop. It makes there's some other little dopey sound. Yeah, okay, sure, that's how it works.
From neutron star mergers, but the evidence has been lacking to know for sure that these gravitational waves and the gamma ray...
For sure. So again, this is all conclusive evidence. We went to trial and we proved our case. You know, we let the opposing side interview our witnesses, and we let them scrutinize our evidence, and we showed them all our crap, and they got to decide, you know, whether this evidence was worthy or not. And we had the trial, and we won. I didn't see any of that take place. I just watched LIGO people go, "We did it!" That's all I see. I don't see any trial taking place first. I certainly don't see you as playing much of a lawyer here. You seem like there's some guy in the stands going, "Yay, yay, they did it!"
Burst came from the same event. The key was to locate where in the sky this neutron star merger occurred.
Right, so they're just showing us all the other location-y thingies based on, now that they have two of these things, they're supposed to be able to do this location thingy much better, but apparently they don't do it very well still. You know, this is looking out, so it has to be somewhere this way looking, well, you know what I mean, if this was the Earth looking out. Not that this picture exactly describes it that way.
Like a merger of black holes, neutron stars emit light when they smash together and continue emitting electromagnetic radiation afterwards.
Okay, now, yes, but it's got to be, you would imagine, a lot less. Like there would be a explosion. There's all kinds of interruptions today. There'd be the explosion, and you'd think that would be, you know, again, they're showing it with these bursts, these gamma ray things going out the side that apparently didn't come our way. Apparently, who knows? So this is just all their theory. So he just talks as if, well, we already know this is exactly how neutron stars collapse, and this is how they crash into each other, and this is what happens when they do. And they don't have any. This is all just drawings. This doesn't have anything to do with a reality. What was the point here? Anyway, let's just continue.
The Fermi Gamma Ray Space Telescope identified a large patch of the sky, roughly the size of 6,000 full moons.
Right, so when they detected those gamma rays, and we're supposed to believe that they found it in all the spectrums. So all the light spectrums, he said earlier, didn't he? Didn't he say that? Didn't he say it was confirmed in all the light spectrums? Well, I guess he doesn't mean it was before they decided where the event was. Once they know where the event was, then they confirmed it with the light. See, so he implied that there was some kind of confirmation ahead of time. So ahead of time, all they had is the Fermi thing with the gamma rays. Yeah, and they have no vision with gamma rays because, you know, they blow up your telescope basically. But anyway, so they can't see much. So they're just saying, okay, it's vaguely in that away. They came from vaguely that away. So that's what we're starting with, vaguely that away.
Using the European Space Agency's integral gamma ray satellite, they were able to narrow down that range.
Right, so the other satellite said somehow there was a big emission could be anywhere in this area, but we didn't get to even know what they saw. What the other did the other telescope also, was it exactly 1.7 seconds after the event that the other telescope saw it? So we don't have that in fact. No, just trust us. I don't think so.
Now, the gravitational waves detected by LIGO allowed them to identify two long strips in the sky, one of which overlapped with the existing search.
So, this is LIGO's, where they say it should have been, and this seems a little strange that it would have those two lines, but whatever, let's just say that's correct.
Area. Now, interestingly, Virgo, which is the newest gravitational wave detector, which is in Italy, it was online at the time, and it should have easily been able to detect these gravitational waves, and yet it saw almost nothing.
Right, so that's not good, but that doesn't mean anything, because that makes it even more proof, because it didn't see it because it was right at its blind spot. Okay, so there's always a catch, right?
And that was kind of a key clue, because it indicated that the gravitational waves must be coming from one of that detector's blind spots. Every interferometer has some blind spots where if the waves are coming at that angle, it's symmetric with respect to the two arms, and so it just can't be detected.
So unfortunately, we didn't get to see any of that. I mean, we don't get to see exactly how they line up on this curved Earth and how they're calculating how these waves travel through the Earth. So we don't get to know any of those details.
So this helped further narrow the search area down to the size of about 144 full moons. Now, within that area, around 50 galaxies were identified to be studied with optical telescopes.
Ah, so now we're doing the optical thing. So this is well after the event, like well after it, quite a while after it, some period of time after, which we're not going to get to know either. Days, weeks, who knows?
And just 11 hours after the initial detection,
Okay, 11 hours after the initial detection. Okay, that's pretty good. So 11 hours after the initial detection, they went to the telescopes and started looking in the area they were told to look in. Okay, it's believable, almost, maybe.
Astronomers located a bright spot in the galaxy NGC 4993. You are seeing here pictures of the light from two neutron stars that merged 130 million.
Well, so that's what he says. So that's what we're seeing. We're seeing pictures of two neutron stars. So they're no brighter than any of these other little dots, by the way. So let's just understand that when one of these neutron stars does this collapsing thing, apparently it makes a dot that's exactly like a lot of these other dots. Exactly the same brightness as those other dots. Now, apparently this is well, let's be careful. This is a star in a galaxy. This is a neutron star in a galaxy. Is the galaxy this little hot thing in the middle? What are we supposed to believe here? So let's back up. A little more, apparently. A little more. A little more. Yeah.
993. You are seeing here pictures of the light from two neutron stars that merged 130 million years ago. Watch how the color and brightness changes in the aftermath of the collision.
And again, just recognize that it just coincidentally happened to be just as bright as all these little stars. So this event that creates a magnitude of energy, that shakes the planet Earth 100 and whatever it was, 130 million light years away, just happens to be no brighter than anything else that happens around there. So it creates a ton more gravity than it creates photons. That would have to be the conclusion, right? So when the neutron stars collapse, it's just lucky for us that it makes a hell of a lot more of this gravity wave stuff than it makes light. Because if it made it in the form of light, if it released the energy in the form of light, it would have burned us all to a crisp.
So what are neutron stars? Well, they're the leftover cores of big stars.
So I don't know why that middle thing was blinking in the end there. It's just a throwaway kind of thing, right? So we had the little star disappear. So I guess they're saying it burned for 11 hours exactly. And I don't know how long those time lapses were. But it just happens that between 11 hours and however long they took those little time lapse pictures, it just happens that's when it turned off. So, lucky again, huh? Just a coincidence. We just happened to be tuning in just when it was turning off. When the fire goes out. Okay. But watch this part. Why does this middle thing go out? Why is it blinking?
Leftover cores of big stars that have exploded.
Did you see that?
Gone
It blinked.
supernova.
Did you see that? It blinked. I saw it blink. What the hell did they do?
Astronomers using a fleet of
I didn't hit no frickin' other video.
What's this little thing?
Watch a fucking
Well, it's
Google
Google Home
commercial.
Mini. You put it in your house and control it with your voice. Hey Google.
You don't pay
Due to
him.
the crazy technological challenges that had to be overcome.
Oh,
in
we
order
already
to
heard
detect
that. You're supposed to be way up
neutron
here.
stars. Well, they're the leftover cores of big stars that have exploded. They've gone supernova. Now,
So we saw that blink, right? Okay, so they're the leftover cores of stars that go supernova. So let's understand. So they're not 30 solar masses. They're not all that crap, right? They're no little bigger than our sun. And somehow they had plenty of mass to convert into gravity waves that could get all the way here. And they didn't just make noise for a little millisecond. They made noise for 100 seconds. So for 100 seconds, they were pushing out a ton of energy for 100 seconds. That's what we're supposed to believe.
those remaining cores are squeezed down by gravity, and if they're too big, say larger than 2 or 3 solar masses, well, they will keep on getting crushed until they collapse in on themselves forever and become a black hole.
Right, so that means if the sun that supernovaed was much bigger than our sun, because he said 2 or 3 solar masses, which means a solar mass is the mass of our sun, then they collapse, and they do this. Everything turns into all the protons and electrons crush into neutrons, which is perfectly, yes, I don't see anything horrible about that idea.
But if those cores are a little smaller, say 1.1 and 1.6 times the mass of our sun, as they were in this case.
Okay, they knew that from that little spot that showed up and disappeared. Somehow he knows all that crap. Sure you do.
Well, then they get squeezed still, and so electrons merge with protons to form neutrons and neutrinos. And the neutrinos take off, and the neutrons are...
Yes, and did we see any of those neutrino thingies? So, all this stuff just takes off. So the neutrinos, another form of energy, just takes off. And now we're going to convert mass into gravity waves, which has, again, nothing to do with Einstein and has nothing to do with the original concept of what a gravity wave was going to be, which was gravity just disturbances in a consistently always existing field of gravity. The gravity doesn't turn off and turn on. Unlike, where light you can turn on and turn off because you can block it completely. Can't block gravity.
Left in a really, really densely packed star. And the only reason the neutrons don't combine with each other is because of a quantum principle, the Pauli exclusion principle, that basically says...
Right, and again, I don't think you need the Pauli exclusion principle to understand that if neutrons are made out of protons and electrons, that there's got to be some limit, because, yes, protons and electrons, by nature, have a component that the electrons aren't going to like, so they can't be mixed. It's like oil and water. It can be the oil and water principle.
You can't put two of these particles right on top of each other, and that's actually the only thing holding that neutron star up. So if you have two of these...
Again, whatever that means, holding that neutron star up. No, the idea of gravity would be holding it together, and gravity, with the argument could be made, is still going to be felt by neutrons. Yeah. Easy. That one's almost easy.
Neutron stars, and they're orbiting each other, well then they emit some of their energy as gravitational waves.
Now, a substantial amount of their energy. Not just some. And again, we haven't heard, for the one that was 5 billion light years away, 3 solar masses were released. So how much of a solar masses was released here? These are both under 1.2 solar masses. So you have a total of 2.5 solar masses to work with. So what percentage of that solar mass, that 2.5, did you convert into these waves that the Earth felt for 100 seconds? Not a millisecond, 100 seconds.
And as they do that, they lose energy, meaning they spiral in closer to each other. And when they get really close, say a few hundred kilometers apart, the gravitational waves become intense.
Right, so again, that's their theory, that when it's spinning like this, it's converting mass. So these things are losing mass as they spin, and the mass is being converted into whatever the form of this energy is. Okay, but this idea, the way they're drawing it in these wave form, is just kind of silly. You're just really talking about two objects, and the fact is the wave would be a little stronger when they're lined up, weaker when they're this way, but we can't see that anyway. So all we're seeing is a line. We're not seeing this spiral crap. We're just seeing the wave line. Anyway, so it's only 2.5 solar masses, yet it created a wave that lasted for 100 seconds.
Us to detect them hundreds of millions of light years away.
Waves that lasted 100 seconds. Sorry, I wanted to make sure that's understood. The waves kept coming for 100 seconds.
way. The collision of neutron stars creates a kilonova, which spews debris out into space. This is debris that glows, allowing us to observe what's been created.
Right. So you're saying that, but first, as the explosion takes place, all of the gravity waves are released before any of that happens. So, again, the process of spinning is converting, is basically breaking electrons and protons down and converting them into some sort of gravity. And then after it completes that, it does this gamma ray burst, and then it does this light thing that apparently lasts some 11 hours. We didn't get to know what those time lapses were, how long it took for it to die out, become invisible again.
And in fact, the new observations with light telescopes have shown that heavy elements like gold, lead, and platinum were made in this event. And that helps us understand where a lot of the heavy elements in our universe come from.
Right, okay, so again, we don't get to see any of that, but okay, fine. So let's just say they can isolate this little bright spot and get just its signature in terms of the the bars of light and darks, and the velocity of the objects themselves, or the velocity of the explosion. You would imagine that the stuff that's lit up, okay, see, when you have light and it's happening as the light goes out, so if it lasts for 11 hours, that means things are burning as they're moving. So it's kind of like a spaceship going into the atmosphere from space, and it gets really hot as it gains all this velocity. It's the same thing going out. There's all this velocity that these little bits have, and as they as they're moving, they're getting hot, and so they burn, and then they glow with light. Now, as they deteriorate from the high velocity they're being ejected at. So that process is, they're claiming that the initial process, just the two things going around, was somehow the more energetic process, and then all this stuff somehow gets to burn later. So it survived the forces that ripped the electrons and the protons to pieces, and that apparently there was still enough of this matter stuff for it to slowly burn many hours later. I don't think so.
In my view, this event really shows us that we're in a new age of astronomy. We can detect gravitational waves, not just from black holes, but now from neutron stars. We can use that.
Yeah, well, whatever. So again, you can make up a theory to fit this whole thing that's just made up. Again, there's no other evidence demonstrating this actually happens, and all you have is this event. Like I say, I don't know how often these gamma ray peaks happen. But you could argue that just coincidence, if they happen every hour or every 15 minutes, you could certainly argue that it would be coincidental. But that's all you got so far. You don't have any other science. There's no other mechanism that demonstrates this creation of gravity waves in any sense where you'd be able to have enough of a change in the gravity. The on-off. Gravity on, gravity off. Because there's no mechanism to do that except this idea of converting matter into gravity and somehow doing it at a cycle. So when something's spinning, two things are spinning around each other, we're also supposed to believe, as that's happening, that there's some even distribution of this gravity bent spacey thing. That it evenly distributes it 360 degrees? I mean, does it have to be pointed at us this way? I mean, do they have to be spinning this way to us, or this way to us, or this way to us? I mean, logically, you'd have to say, do you know the orientation? Are you really saying that in a completely spherical, in all 360 degrees, in all facets of the universe, it's creating the exact same on-off pattern of emission? That wouldn't be possible. So they'd have to be spinning at this angle to us. Anyway. And why didn't they move anything around them? Can we watch everything get moved around them because it's so much energy?
Information to locate places in the sky where that occurred, and we can validate that with our other telescopes looking in all parts of the electromagnetic spectrum. So now we really have more tools.
So again, this whole thing of looking in all spectrums, blah, 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 that didn't happen until well after the event. And they're just talking about they saw something that went from light to dark, which happens all the time in the universe. I mean, supernovas glow and then they go out. And stuff turns on and it turns off all the time. But he's saying that somehow when we see that, we verified it in all the spectrum, and therefore we can say that that verifies that what they saw with the optical telescope is somehow proof that that event was the thing that produced the wave in the first place, and that there's some reason to believe nothing else could have been the cause. It's conclusive evidence, not merely circumstantial.
To understand our universe, and I just can't wait for the questions that we're going to address next, and all of the different things we're going to be able to study.
Oh, it'll be something like dark matter or something, and some other bullshit you people make up. I mean, this is, you know, oh, he's just so happy about it. Oh, I'm so happy I get to make up shit for a living. So much fun.
As the gravitational wave observatories get better and better, it's a phenomenal time to be studying the universe.
Yeah, whatever. To be making the universe up. You're not studying anything that's real. You're studying your own, what's the word they use for when people anthropomorphize? You're human-formorphizing the universe. You're making it in your own image, you know, what you want it to be. What your happiest little fun dreams are for it to be. And that's all you're doing. And you're finding little tiny bits of evidence that might indicate your little fantasy is true. But it's just tiny bits of evidence. You know, crap. Crappy-asium. Crappy-asium. Yeah, maybe that's what I'll call them. Crappy-asium. Bullshit, I call. But anyway. So I have to get more details. So small amount of mass somehow creates a wave for a longer period of time, more energy for a longer period of time. Now I'm not saying more energy is a little tricky, you know, but it has to be in some ways or they couldn't have detected it. So, you know, I'm trying to find the chart of the comparison. Yeah, this. So this line over time, it gets gradually thicker. See, it does get thicker. Starts off there. And they make that into a chirp, which isn't very chirpy. But you'd have to argue, even by the proportions drawn here, that there's a lot more stuff in this long yellow line than there is stuff in that blue line. Because that blue line, that green line should be much bigger then. So we're not getting anything to scale or proportion. It's just, you know, just make it all fit and look colorful, I guess. But again, theoretic. So their theory is so broad that it can allow events to do this, and then do this. Actually, twice that. And we're supposed to believe it fits right in with the theory. That's not aberrant to the circumstance at all. No, not at all. Yeah. I mean, right there's reason to say, wait a minute. Alright, anyway, until next time. I mean, it's just not good enough to talk as if you know this is what you're doing. I mean, it really should be tested somehow. I wish I could make earth noises just to see if I can make a noise and they'll hear it and go, oh, we just heard a black hole, blah, 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 and then I could just show up and say, no, you didn't. Alright. That would be fun. Anyway, till next time. So.